should have turned that off. Cool. So we talked, last time about the river continuum concept, and no celebration today. Sorry. I'm sorry, you guys. I'm sorry. And can I reach that far? I can. I think I can. Will that do it? Ha! Perfect. All right. Oh, sorry, Elijah. Nothing personal. There was just somebody was beginning to use a jackhammer in the hallway, and so we wanted to get some space. So today we're going to be talking a little bit about more about like the physical template of the stream. If you remember, Vinod et al. In the RCC talked about this idea that we can think of the stream and the river as a changing physical gradient and associated biotic adjustments. So we have these physical processes going on, and then our biotic community is responding. So we'll be talking a little bit big picture about some of these processes. And it's always striking when you see two streams or rivers come together that differ greatly in their coloration. And that can be due to all sorts of things. The geology of the area. Up in the Himalayas, glacier-fed rivers have kind of like a milky coloration because of the sediment they're pulling in. So what we have moving down the stream physically can vary a lot from place to place. But just to kind of set the concept again, this idea, right, in the river continuum concept that there's so much in that paper. I mean, so much in that paper that sometimes it's hard to see the forest for the trees, so to speak. What's the stream analogy? River for the streams. Hard to see the boulders for the sand. I don't know. It's hard to see the chironomid larva for the odonate larva. I don't know. Come up with your own perspective thing. But in the RCC, one of the big concepts just to keep in mind is that we need to think of this gradient of physical factors. And so as we're trying to understand what else is going on in the river or stream, we always want to think big picture, like where are we? What are the physical processes affecting us? So today, again, talk a little bit about that in more detail. So just a couple terms to make sure we're on the same page. Fluvial, I think we talked about, but just to give you a little more formal definition, it has to do with flowing water. So something that has to do with a river or is found in a river is our definition of fluvial. And then geomorphology. What does morphology refer to? Say that again, Michael. Shape. Yeah, absolutely. I had a real hard time understanding myself when on the video the other day. I hope something I say is legible because it's really hard to hear what people are saying with these masks on. Yeah. That could be. That thing, it was like, I think my nose is a little shorter than it was before I put that thing on. It's like, anyway. Yeah, exactly. So form, and so when we talk about, what is this? Like every 5 clicks it works. So form and shape, but so geomorphology is sort of the physical features of the surface of the earth, in particular their shape in relation to geological structures. How do we define geological? Yeah, rocks, say that again? Yeah, so I was hoping we had a real formal definition that the earth scientists use. We probably do. So geology, just the study of rocks and minerals that make up the earth, right? So surprise, right? It's all tied together, right? All 3 of our concentrations and environmental studies tie together, you guys. It's like the Lion King again, that circle of life. Anybody see the new Lion King? I have not. I know the way it ends and everything else and all that stuff. Okay, so so fluvial geomorphology then. It has to do with the physical features on the surface of the earth and how those relate to rivers. I see a couple folks still jotting down notes, so I'll pause for a moment here. Anybody find themselves driving over like a river on a little bridge and wondering like what's under there now, We're like before, I'm always jealous of ornithologists because you can see the stuff that you study just like walking across campus. It's like, what birds are there, what's coming in the chimney, you can just look. Stream ecology, we got to get in there and like turn over rocks, pull nets, all that kind of stuff. But yeah, I'm that guy who whenever I'm driving over a river or stream, I start to wonder what's inside there. So hopefully you're starting to have those thoughts as you're driving over rivers and streams or walking through them or falling into them, however you're experiencing them. This thing is really, must need a battery change or something here. Okay, so here's our ecological address, if you will, the Upper French Broad watershed. Again, it's a bizarre river, right? Because it flows north, and one of the oldest rivers in the world. Estimates vary, but it flows through the Appalachians rather than out of the Appalachians. Is the crazy thing about it. So it arises near Rosman in Transylvania County, flows north, and it picks up all these rivers along the way. So the Little River, Davidson River, Mills River, Mudge Creek, Cane Creek. Here's the Swannanoa watershed where we're working, of course. I've got Flat Creek here coming out of the hills. Hominy Creek, Newfound Creek, Reams Creek, Flat Creek. Here's our tiny little Glens Creek, our little UNCA stream. Sandy Mush, Ivy River, Big Laurel, Spring, right? As we're coming in here, all of these stream networks are coming into the French Broad. If we look a little closer, we can see a little more of the Swannanoa here. And we've got our tributary right in here, which is Sweeten Creek. So we mentioned stream order the other day, right? And just this idea that the smallest perennial stream is first order. So we don't need to talk too much about that. If you were to look at the map of a watershed, what we call a drainage network, that lists out all the tributaries based on stream order, looks something like this. So in our watershed, first of all, we want to think of, is it mostly made up of small or large streams? Small streams, absolutely. So the majority of our drainage network, as we might call it, is made up of these tiny little first order streams. So you'll hear the word headwater streams used to refer to the far upstream reaches of a watershed. And so in general, these things make up over 70% of the stream network. And we're just talking about distance here, right? So like if we were to add up the distance of like all the streams in our watershed, about 70% of the distance would be first order, would be these headwater streams. And an important thing to keep in mind is the high surface area to volume ratio. So again, when it's flowing through a forest, there's a lot of ways that the land can connect with the water there. There's a lot of ways. Most of those water molecules are going to be associated with either the bottom of the stream, the air surface, or the edge of the stream somehow. So why might this be important? What's going to be happening in these headwater streams that might be important for the rest of the watershed? Any thoughts? Yeah, so the interaction with the stream bed, there's going to be a lot of erosion and a lot of input of minerals here. And these are often fairly high gradient areas, so we've got more erosive power and so ions entering here. If you have sedimentary rock, which we don't have a lot of around here, most of our bedrock is igneous or metamorphic, but you can have a lot of nutrient input. So yeah, and when it comes in contact with the air, of course, you have gas exchange going on. What else? We talked in the RCC the other day about the RCC, right? That this is a place where a lot of, relatively speaking, a lot of material is coming in from outside into the stream. What else might be happening here that's important? Mm-hmm. Yeah, exactly. streams, again, they're unidirectional ecosystems, right? So yeah, whatever goes on up here affects everything downstream. Some of y'all were in the environmental restoration class last semester. One of the big lessons in stream restoration is that it doesn't matter what I do in this little section of the stream if the water that's coming in is in bad shape, you know? And that's because what goes on upstream affects the rest of the watershed, absolutely. So a couple of things that are particularly important here, and this is a theme that we'll talk about later as well, but a lot of nutrient retention happens here. Why might we have our stream taking up more nutrients in the headwaters than further downstream? Any thoughts? Yeah, exactly. If you think of the water that contains a certain amount of nutrients, those nutrients are going to get taken up by algae and biofilms on the rocks. And so there's going to be more water in contact with that substrate, relatively speaking, in these headwaters. So the vast amount of nutrient uptake in streams takes place in these headwaters. We talked about this in the RCC already, but organic matter processing, right? We're going to have the largest input of leaves and things, of course, and then the breaking down of that into smaller and smaller pieces as we go along. So organic matter processing. And just this connection with a terrestrial ecosystem, I think I mentioned in passing that Sweeten Creek, you know, if there aren't many invertebrates living in that stream, well, how is it that fishes and things can live there? One of the reasons is because there's input from the terrestrial ecosystem into that stream. My feeling is that when we look at the fishes that are able to live there, we're probably going to find fishes that are able to exist on energy that comes in from the terrestrial ecosystem. That we're probably not going to find things like sculpins and things like darters and, you know, that are feeding on invertebrates in the stream. They've got downturned mouths. They're living in that stream, feeding off of the stream production. We're probably going to find stuff that can only survive with terrestrial input. Now, that's kind of a downstream site, but I think it's kind of out of necessity there that terrestrial input is going to be important. So this is real important. Another interesting thing that happens, where do you think most of our pollution occurs? In the headwaters or further downstream in general? Yeah, it's generally further downstream. Why do you think that might be? Yeah, absolutely. Yep. We look at these high elevation sites. It's tough to build there. Further downstream is where we're going to be building our towns and our cities. And something we see a lot here in the mountains where we do our agriculture, right? We do our agriculture in these valleys along the side of the streams. So these headwater streams are relatively pristine. So another thing that we see is that when the downstream areas start to become polluted and degraded, these headwater areas serve as refugia for those species to move up into the watershed. Now, you got to be able to live in a habitat like this as opposed to what you had downstream. But if you can, then you're in good shape. So they're important that way too. But what do you think about the sensitivity of these headwater streams to disturbance? You think it's higher or lower than further downstream? Higher. Why do you think higher? What makes you think that? Yeah, that's probably the biggest reason, right? That they're more easier to pollute. So if we were to, for instance, take these trees out of the riparian zone here, this stream could get filled in pretty quick with sediment. There's just less water to clean it out. So these are real sensitive to disturbance. So, you know, part of me wants to go and explore upstream in the Sweeten Creek watershed and just see what it looks like, because I don't know, to be honest. We can look at the map and see what the Beachy Creek headwaters look like. You know, it's up there on the Parkway, in the Asheville watershed, and then Pisgah. But I don't know, man. I wonder what the headwaters look like in Sweeten Creek. Like, I wonder if it's like just somebody's yard. You know, I don't know. So it'd be interesting to know. Because, right, so when you do have these disturbances up in the headwaters, then all these things don't happen well. All these things don't happen well, and then, as was mentioned, that leads to problems downstream. So these headwaters are super important. And, you know, again, luckily enough, we don't like to develop headwaters as much as lower sections generally. But when we do, it has pretty big problems. So these are the furthest areas. So if we look at what stream channels look like as they move downstream, you know, oh shoot, did it? Is there an earlier version of this? Hold on one second. I apologize. I want to talk about one other thing before that. I really hope that I got that the way I wanted to. We'll see here how this goes. Okay, so when we look at, as it flows downstream, what that channel starts to look like, what is going to determine the shape of that river channel and how it looks? Yeah, flow velocity is going to be a big one. That's, I guess kind of half of the story right there, right, is the flow velocity, what that looks like. Yeah, the particles that are suspended in the water. Topography, yeah. So you can kind of think of it this way, like the first is like how that stream is geologically constrained or not. And so that can happen a bunch of different ways. Then the other part is this kind of equilibrium between discharge and sediment flow. And so I'll show you a couple examples of that in just a second here. But, you know, we look at what the channel looks like in Sweeten Creek versus Beachy Creek. And the site where we were at Beachy Creek, it was a little bit atypical because we've got, you know, a parking lot on one side and we've got, you know, a mowed area on the other. That stream isn't going to be able to move as easily as it could further upstream, but much different from Sweeten Creek, where we've got, you know, parking lots on both sides. So what we often see in a stream as it moves downstream is an alluvial plain. So alluvium are deposits left by flowing streams. So think of a river valley, right? You can kind of think of like the French Broad River Valley. Think of the Swannanoa Valley. You know, I-70 essentially, I-70 and I-40 essentially both follow the Swannanoa River Valley up, right? And so those are areas, that valley is an area where there's lots of the fine particulate matter that's been left over the eons from rivers flowing through there. And those rivers have changed shape and changed direction over the years. But as they've done that, they've left a lot of these fine, what we call alluvial deposits. And you don't need to know everything in this cartoon here, but just realize that what we have here is a valley of fairly fine, fairly fine diameter substrate that's deposited here. So when we have a river in a valley like this, it's going to be free to meander back and forth. So on an alluvial plain, we have a fairly flat area and small particle size, and that doesn't constrain the river a whole lot. So when that happens, we get this kind of meandering stream here. Now, why does a stream meander? Why doesn't it just flow straight? Any thoughts? Yeah. So there are going to be there's going to be micro variations in the erosibility, right? The resistance along this path. And so when it hits an area where there's a lot of resistance, it turns the other way. And as it turns, it changes velocity, right? There are differences in velocity in different parts of that river. And the change in velocity determines what size of particles that river is going to be able to hold. And of course, as the velocity slows, what happens to the particles? They settle out, right? And so there's this settling out of particles in the slow velocity areas of that stream. Whereas where there's higher flow velocity, not only are you going to keep those particles constrained, entrained in the water, but you're going to have enough force to actually erode more particles out. So what happens is, on the outside of this bend, do you have more or less power from the stream? More. Imagine, you're sitting in the car with like your brothers and sisters, and there's like 3 of you in the back seat, and you're on the right side, and the car turns to the left. Man, I see they like, did you guys do that? You like elbow them like into the door. Ha ha ha, got you. Then you turn to the right. It's the person on the other side that gets nailed in the door. Yeah, so there's more force on the outside of that curve, right? So that more force causes more and more erosion to happen on that outside bend. But on the inside of that bend, there's less velocity. And so that's where the sediment settles out. And so we have, over time, these meanders getting more and more extreme as they erode further and further out on the outside bend, and as they deposit more and more sediment on the inside bend. And then as they get further and further to the side, under normal flow conditions, what can happen is then you get the crazy flood coming through, and rivers are lazy like all of us. They want to take a shortcut. And so when we get a lot of water coming down all at once, instead of going side to side to side to side, it's got enough power that it can cut straight through here. This water comes down here with a lot more power, cuts straight through. And when that river cuts straight through, then it can isolate this meander in the channel. And then over time, by depositing sediment, it can cut that off and can form these oxbow lakes. So this, what's called an oxbow lake, is an old meander that got cut off. And that happens when you have sort of alluvial deposits that river is flowing through, and it can just kind of keep doing its thing. There's no boulders, there's not a ton of bedrock to constrain it. It just keeps doing its thing, flowing and flowing and flowing, getting more and more and more extreme until it gets cut off, right? So we have this sort of meandering channel in an alluvial valley, alluvial plain or alluvial valley. So we have this kind of, and you see this when you're driving. I don't know if you've ever been in a plane flying over. I'm always looking at rivers and lakes. That's just me, and you can see this when you look down. It's like, oh, cool. You can see this if we look back at the French Broad River as well. Okay, so if we were to take a cross section of these streams, then we have a term here. This term, knowledge of this term got me a job back when I was in grad school. I didn't end up taking that job. It's a long story. But there's this term called the thalweg. Can you see that okay? It's T-H-A-L-W-E-G. Bless you. The thalweg. That's the location of the maximum depth in the channel. And so I was interviewing for a position on the Kansas Department of Parks and Wildlife stream team. It's kind of cool. You'd spend the whole summer visiting sites and seining for fish. And one of the things you had to do is measure the thalweg. They like put you up in a hotel or motels, and it's kind of cool. But I ended up working as a summer park ranger for the Army Corps of Engineers, which is a whole other adventure. I'll tell you about it sometime. But they asked, what is the thalweg? And I said, well, let me tell you, I know what the thalweg is. It's the deepest part of the channel. All right, so this is what we call the thalweg. It's the area of maximum depth in the channel. And the location of that thalweg in the channel varies depending on what part of the meander we're in. So it's only when it's flowing straight down that the thalweg is in the middle of the channel. When it's meandering, then, if you look at, this meander into the outside here, right? Our thalweg is going to be to the outside bend of the bend, and shallow here, right? So, so this thalweg then, the location is gonna move from place to place. Yeah. So yeah, so that's the thing, right? So this is kind of like, have you heard of like what's called a straw man? Like it's a model, it makes sense and logically follows, but is not often the case, right? Like you can knock it down pretty good, like a straw man. So like next time you see, what is a straw man? Are they like scarecrows? So next time you see a scarecrow out in the field, just to test the idea that a straw man is a theory that's easily knocked down, just go into that field, try to knock it down, just see what happens. Right? And if you knock it down easily, then like it makes sense, this whole idea of the straw man. And then run. I recommend you do this at night. No, I'm kidding. Or you make your own straw man. But who wants to go to all the trouble of making a straw man if it's just going to get knocked down? I don't know. You got nothing else to do except make straw men. But anyway. And Dorothy, what does the straw man need in The Wizard of Oz? Do you know what it is? A brain. Okay. So maybe you can like give it a brain or something while you're doing it, because the straw man will appreciate that. Because there's no brain. The Wizard of Oz, as it relates to like intellectual theory, we could go with that. We could go with that quite a ways. They get weird. They get a little weird. Like, why does it all turn into color at one time? Like, is that when people like suddenly figure things out? That's always weird. You're like, wait, I thought this movie was... All right. So we can get channels that look really different, and you don't need to know really any of this, but just to show an example of how channels can look very different. And this is from a cartoon put together by Dave Rosgen, who's really involved in the practice of stream restoration. And for stream restoration to work, you have to know what kind of channel you're recreating. And so there's a lot of measurements that go into saying, what should that natural channel look like? And a few different kinds here. We'll go into why those are. But there are some real detailed calculations of the width to depth ratio, the slope, what's called the sinuosity, which just means like how extreme is the curve relative to the straight line distance. So stream channels can look really different. So here's the interesting thing. When streams are not constrained by valleys or dam building or anything else, they follow a wavelength that is amazingly consistent. So the wavelength, right, which means one complete wave. So a meander one way, back, a meander the other way, and back, that whole wavelength. It's almost always 10 to 14 times the channel width, no matter the amount of water, which is, it's kind of crazy how that goes. So that's whether that's the Amazon River or just like some water that's leaked in under your door and is like flowing down your floor, which is not completely level. So that's crazy. This is kind of like a property of water. There's an area here that might be a candidate to become an oxbow lake pretty soon, right? When this water comes rushing down here higher than normal. So this is actually something, why would it be important to know about this as a stream ecologist? Any thoughts? Say we're studying, we want to be able to adequately measure like the invertebrate community or the fish community or the available habitat. How might this be important to us? Any thoughts? Yeah, good. So like if we think of the stream as sort of like repeating itself in like wavelength segments, then if we've sampled the whole wavelength, like a meander this way, a meander that way and back, then you could argue, we've done a pretty good job of sampling all the habitats that are there. Because if we just go back to our cartoon here, that the habitat here is going to be different from the habitat here. So if I go and I just sample here and I'm like, yep, I know what the stream is like. I know what the habitat's like. I haven't sampled all of it. So an interesting consequence of this has to do with the formation of riffles and pools. And we've seen already, particularly in Sweeten Creek, just how different riffles and pools are. The invertebrate community is different. As we'll find out, the fish community is different. Nutrient processing is different. Why might nutrient processing be different in riffles versus pools? Any thoughts? Say it again. Yeah, so oxygenation, right? We're getting mixing of water with the air here. Absolutely. And if we think about, like, for instance, nutrient uptake, it's going to be taken up by algae. Algae and what we call periphyton, the plants that live in association with the rocks. In this pool, what kind of substrate do we have? It's kind of written right here. Silt and sand, the finer stuff, right? The finer substrates in life are found in the pools. The rougher substrates in life are found in the riffles, right? So where are we going to have more periphyte and more algae growing on stable rocks or unstable silt and sand? Stable rocks, exactly. So these riffles then are real important for places where nutrient uptake is going on. So bottom line is riffles and pools are very different ecologically, and they can be very close to one another as we've seen in our sites. So the interesting thing about it is, if we think of like our meanders, on average, these riffles are going to be formed every time we have a meander, right? So there's going to be deposition on the inside of that bend, and we have a lot of riffles form on the inside of meanders where it deposits that substrate. So on average, riffles are formed about every 5 to 7 channel widths. So about half of that meander, if that makes sense. So if I want to quantify all the available habitat, then, I want to make sure that I'm sampling more than this. So depending on what you're doing, some folks say that if you're sampling a river or stream, your sample length should be somewhere between 10 and 12 channel widths, just to make sure you've sampled all the available habitat. Now, does that make sense with the sites that we've looked at? Are you guys thumbs up on that idea or thumbs down? What do you think? What have been some of the unique kind of habitats we've seen in our streams so far? And remember, this is talking about alluvial plain, like nothing else going down. But at our sites, do you think we could apply that rule? Olivia's saying no. Why? Because of the way I asked the question? No. Yeah. Yeah, so you always need to give your site a look over and kind of see what the habitat's like. I don't know if I don't think everybody went far enough upstream at Beetree Creek. But did you see that ginormous pool? That's a technical term, ginormous. I'll define it later. Did you see that huge pool under the bridge upstream? That's an atypical habitat, right? That wasn't anywhere else in our section, and it was there because of the way that bridge was built. And if you notice, what was upstream of that pool, those of y'all that were up there? Flat, shallow is a big riffle, right? So we had a lot of water power coming down there. Then it hits that bridge, doesn't have anywhere to go, so it just scours it out, right? Scours it out, keeps going. So if we don't have anything going on, like a giant chunk of cement that we put in, or whatever, a railroad trestle, then this can work. But you always want to kind of do the eyeball test when you're out at a stream site and say, what are the habitats really like here? Like, okay, this certainly makes sense, but what am I missing if I just sample like 10 channel widths and it doesn't include that big pool at the bridge, right, or something like that? Okay, yeah. So anyway, when streams are more constrained, other things happen. One interesting thing here is sort of a natural process, and that is woody debris. It's been argued that one of the biggest changes that humans have done to rivers and streams since industrialization, essentially, is taking woody debris out of rivers and streams. We don't like it. If it's in a navigable stream, we take it out because we can't move. We can't, get our barges and boats by it. And so there's some really interesting data showing that, back in the day, there were just a lot more trees falling in our streams, and they just stayed there, right? And they created these way different habitats than what we see now. But this is just a graph looking at average spacing between pools as a function of the amount of wood in the river. And so, as one might expect, when you get more and more wood, your pools become closer and closer together. So that's another thing, that happens. You know, beaver dams used to be everywhere. I mean, everywhere. Like, and that was just a whole different landscape. We don't like beavers so much. We don't like dynamic ecosystems, right? And so when a beaver builds a dam and it floods the creek, and you got houses with yards next to the creek, we clear it out, right? So so we try to take the dynamism out of these ecosystems, but naturally there's quite a bit, including this. Just a couple pictures of Glens Creek and kind of what this looks like to be thinking a bit about channel formation and constrained channels or not. So one of the consequences of that meandering stream is that it's dampening the power of that river, right? What's an analogy, right? It's like, imagine a NASCAR race that was just like, how many miles do they go in NASCAR race? It's 500 laps, right? How big is the track? Like a mile? I don't know. Well, I don't know. Say that you've got like, I'm making this up. Say you've got like a 100-mile NASCAR race. So imagine they do it on like a 100-mile straight line. Pedal them out, very dangerous. But instead, we've got this track, right? Which makes them go a lot slower. So when we take the meanders out of a stream, as we like to do in urban areas, we have a lot more power in that stream, a lot more erosive power. And when that stream does hit erosible materials, it tears the heck out of it. And so this is a picture from Glens Creek right here on campus. And you look at all the fine sediment here in the stream. And so part of that is going to be washed in from the landscape, but a lot of it's going to be due to massively high rates of erosion, because that water is hauling down the channel with a lot more power than it would if we'd had a natural meandering channel upstream instead of channelized, constrained little stream sections. So we have a lot of erosion here. Another picture showing that whenever we see what's called an incised bank, a very steep bank, right? That tells you there's more erosion going on than normal because the power of that stream is more than it should be, right? And also, when we see so much sediment in here, that tells you, of course, that there's more sediment that can be washed downstream, and you know, we're going to need a really big flood to take this out. And when we do that, more sediment's going to come in. So we can get a couple different kinds of channels as well. We can get what's called a braided channel. And a braided channel is basically made up of lots of little channels. And we see this where there's a high amount of fluctuation in discharge and flow. Any idea why that might happen? Why wouldn't we have just one? Like, what would it be about having a lot of fluctuation and flow that causes our channel to look like this? Any thoughts? And as you're thinking about that, I'll show a picture of a braided channel, someplace where we did research, up at about 12,000 foot site in Nepal. A hint is that this is kind of at the foot of the mountains. Yeah. Fed by snowmelt. And so when it's melting, you get, of course, really high flow rates off of these mountains, carrying a lot of sediment. And then it hits the flat area, and what happens to that flow velocity? Goes way down. And of course, what happens under the ability to transport sediments when it slows down a lot? It drops down, right? So it drops all that sediment. When it drops all that sediment, all of a sudden, you know, you've got a very shallow, wide channel. And so then it starts kind of like eroding little channelets through that. Another way you can see this is when there's high temporal variation, like if there's, for instance, downstream in the monsoon, where the monsoon is carrying all this sediment down, and then the water levels start to drop because the rain stops. And so the power to carry that sediment is reduced. It drops all that sediment, right? And then as the water lowers, it sort of carves little small stream channels through that. So yeah, so these braided channels can occur when they look like this. We don't see too many of these around here. All right, but these are what channels can look like when we start constraining them. So this is the Missouri River. Just like no rivers look like this. Long, straight. Nah, not gonna be real. We spent billions of dollars in the middle part of the 20th century straightening a lot of rivers, because the thought was you're going to get that flood water off of the land quicker. But what's the downside of getting all that flood water off the land quickly? High velocity. It's going downstream really fast. It's a problem, and we learned about that later. And we learned that really what we want to do, if you can design your own channel, is to build these meanders in, so that you might have erosion, you might have some dynamic stuff going on, but you're reducing the power of that water. So you reduce the downstream flooding, erosion, things like that. You see a lot of these. This is what we might call an armored channel. Wherever we build roads next to streams, we like to do this, right? You put a whole bunch of rocks and stuff in here, big rocks, and you force that stream to take a sharp turn, to constrain that channel. So when that happens, again, whenever you look at a channel, think about where is the power going, right? Think about where is the power going. Because if it's hitting something that can't erode, then it's not releasing any of that power. And so that power is going to keep going downstream. And so, yeah, that's why we have that crazy, that pool right there at Beetree Creek, because that power is going down when it hits that cement and moves to the right. So we see a lot of these. And again, you can drive around Asheville, see this. We can look at Sweeten Creek and see this. That channel's not going anywhere in Sweeten Creek. It's got parking lots on both sides, right? Armored, steep. We've essentially determined. Now, what do you think happens to habitat diversity in a channel like this versus the more meandering channel? Yeah, goes way down. So if you think of more habitats equals more niches equals more species, when we do this, we've lost all those backwater slow habitats. We've lost all those riffles. So it's not surprising to see a decline in species diversity when you put something like this in. Well, we've modified rivers in all kinds of ways, and our discussion paper for today is going to address that in a little more detail. But it's interesting to think about how the movement of stream channels affects the terrestrial environment too. So this is tamarisk or salt cedar, which is an invasive plant species out in the West. And this is in the Grand Canyon, so the Colorado River, at the end of the 19th century and the late 1900s. And this is a non-native species. And so normally there would be high fluctuations in water flow and migration of the channel, although very slowly in the Grand Canyon for sure. And it kept these substrates unstable. When that went away, all of a sudden we had this invasive species, which you can't see very well, but it's a shrub, an invasive shrub that gets established here. So in the back of your mind, you should be thinking, when we change anything about a river, including the channel pattern and the flow regime, it's going to affect the species that can live there. And I think Torn and I were talking, I guess, in the van on the way back the other day about how, that is why non-native and invasive species do so very well in disturbed habitats. It's because it's no longer a habitat that's good for the native species. Cool. So one part of our riverine physical process that's been affected to a great degree is sediment transport. And so this is an aerial photo of the mouth of the Mississippi. And it's been estimated that over the last couple thousand years, the Mississippi Delta has moved over 100 miles out into the Gulf of Mexico because of this transport of sediment, which is always being deposited over the years by the Mississippi. But things have changed a little bit. Any questions or comments before we take a 5-minute break and then discuss the Savitsky paper.